All right, then. So, my apologies. We had a small technical issue with our microphone input. So, as I was saying, today we will be looking at Fusion and taking a couple of steps back compared to some of our other more advanced projects. We will be looking at specifically what is necessary to get your project off the ground and get your first multiplayer functionalities working. Now, in order to do this, we have decided to pick up and remake one of our most popular demo samples from all the way back to PUN Classic, called Asteroids. Hey, thank you all for joining. Looks like we definitely even have a couple of our colleagues over from Japan and Korea, so thank you for tuning in today. And in order to keep things simple, we will be going for straightforward use cases as well as host mode rather than shared or server mode. Now, dedicated server mode is of course the one that you would want to use if you were to host dedicated servers, but that is rarely necessary when you start. And shared mode, although more similar to the original demos, is a lot more complicated because you have multiple sources of truth for your different states. That is why we have decided to stay on host mode, since that is the one that is the easiest to get into when you first start working, not only in multiplayer, but also with Fusion in general. So, with no further ado, let's dive into it. We have here a look at my editor, and we will also have the Unity editor here for you in order to see how it actually looks like in the editor, as well as a couple of diagrams to look at in order to see how these things can be structured from just a logical point of view. So, let's break down asteroids. And of course, what we all want to start with is very much the start, in this case, the menu. If you want to actually build a menu, and more importantly, start a game session using Fusion, there are two things to take into consideration. One, will the person starting the session, or starting their session more specifically, be the one hosting it? Or rather, will they be joining an existing session? Now, of course, in the menu itself, that is very easy. We simply have a button to start as a host or to start a client. Now, we need also to keep in mind two additional things for this. One is, how is the player identified? Usually, that would mean a nickname. For the sake of this demonstration, we will simply allow the user to choose a nickname or just take the one that we have automatically and fairly randomly generated for them. The second part is, of course, when you do start your session, whether it is as the host or by joining as a client, you have to know which session are you joining, or do you not care at all? If you want to host a session with a specific name, this will be the name that other friends of yours, for instance, can choose in order to join it as well. It is the identifier, for the lack of a better word. On the other hand, if you don't give a name to your session, it will just be given a random ID on our servers. If, as a client, you decide to not specify a name for the session that you'd like to be joining, it will simply look for a random session. So, what does that mean in terms of functionality when we stay in Unity? Well, of course, we have the canvas with the start menu. All of our buttons are just regular buttons. And as it is common here, the important part is not what the button says on itself, but much rather what it actually does when you click on it. In this case, both the Start Host and the Start Client button are linked to the Start Menu script, which provides a couple of public functions that will be triggered once this button is clicked on. In addition to that, it of course also has a couple of public fields in order to get the name of the room and of the player. So if we open this very shortly, we will now see that in the editor itself, we have, of course, our serialized properties to be filled out, which are not particularly relevant to our topic at hand. But we also have here the method implementations. So the methods have one common goal, and that's that they call start game. Start game is the fundamental and most important method to call on your network runner when you first start your session. It will define what the game mode is. So in our case, it could be either host or start as a client if the session already exists, or just client. Or if you want to be even more restrictive, you could, of course, also simply start as a host. But that is usually not advisable, since if you have a session with the same name, you might want to join it or not. But those are edge cases you don't really have to worry at first. So what do we actually need to do in order to start the game? Well, first of all, we need a network runner. The network runner itself, if it doesn't exist yet, needs to be created. Once it's been created, we also need to tell, oh, by the way, please tell me if you can actually read the code on screen, as I usually don't have it that big. So, returning back to the subject at hand. Once we have created the runner, we need to tell it whether or not the client that we're starting here will be providing input to the game session. Now, there are only two instances where you want to provide input. That is, or actually, one single instance. That is the one where you have a player that actually can control something within the game session that is currently running. When I say to before, I was referring to the fact that as a host, you're running a server, which usually doesn't need to provide input, but you also run a client in addition to that, which does have to provide input. So in this case, you simply set this variable to true in order to be able to tell the game session, hey, my client is connecting and has the ability of providing input. And then, as we said, we need to actually define the start arguments for the game session itself. The two most important ones are the arguments that we have already mentioned before, the game mode, and of course, the session name, which can be either nothing or specified. Once we do this, we can actually tell the runner, okay, with this information, please do start a game session for us. Now, this is an async method, meaning it will only continue executing once it has properly been able to start the game. And this is done in the background by connecting to our servers, connecting to the session, and a bunch of other more advanced technical aspects that I will not bore you with today. Now, this is okay, cool. We have the game session running and connected to whomever is hosting the game. Now, the thing that we need to do next is, of course, load, or rather, set the next scene that the gameplay happens in. For the purposes of this demonstration, once again, we're using the most simple method available to us, which is set active scenes, or set active scene through the runner instance. Now, although it is the most convenient one to use, it comes with several restrictions that need to be made clear, because it might not scale if you want multiple scene loading or additive scene loading. Set active scene simply checks, okay, is this scene that you're requesting already the one that is currently active as per the runner's information? If it is, this method will not do anything, which means if you're trying to reload the same scene you're already currently on, this is not the right choice. However, if you're going from one menu scene to the now game scene, and it just realizes, okay, these are two separate scenes, we agree we can load the scene as the next one. So, in short, only use set active scene if, number one, you're loading only one scene at a time, and number two, you are sure that the scene that you're asking to be loaded is different than the one that you're currently on. Now, as we mentioned before, this is what you need to start the session. But as we also know, there is some additional information that we would like to keep and inform the other players when we join the session about. And the most important piece of information, or the most requested one, is of course the player nickname. So let's take a look shortly at what that is. In our scenario, the player nickname is made of, well, simply a text field. We can open it here. It has the text area with the placeholder text that is populated by our nickname generation script, which in itself is very trivial in that it just generates 4 numbers to append to the player name. And then we of course have the regular text field where people can enter their desired nickname. As you may notice, in here, we do not actually save it anywhere. That is because the only time that we actually care about what has been entered here is when somebody actually does click the start host button or the start client button, which is why it is here again read immediately in the start host and start client methods. Right, so before we move on to the nickname, Zachary here is asking a very good question, and that is, what's the difference between set active scene and the actual scene argument that you would be able to pass in as part of the start arguments? I have not displayed that, but if we were to go down to the actual start games struct, we could here have a scene which takes a scene ref. Now, the reasons as to why we are using set active scene were already explained. It is simply the simplest methods to load that. You could technically request that as well through the start game arguments. However, the start game arguments do not do any safety check as to whether this scene is already available in memory or not, whereas set active scene does. That means, unless this scene has already been loaded once by the scene manager, it will not properly load this. This is a limitation within the scene manager available within Unity itself, as there are different method calls depending on whether or not you're trying to load by build index, by scene index, or by path. And so this is totally possible, but adds a layer of complexity that was not desired for the simple version of the remake. We will present a more complete version of scene loading with an upcoming sample, as well as an advanced version of the Fusion Asteroids sample at a later date. I hope that answers your question, Zachary. So, returning to what I mentioned before regarding the nickname itself. Now, we have simply called the method setPlayerData because, of course, there could be additional data that you'd like to persist between your menu and your actual game scene and inform the other players. Now, this could be anything from, for instance, which skin did you choose as a player, which character, and other configuration aspects of your game or the controlling aspects for your player. In this case, we simply encapsulate the data in one object that we call player data. Player data itself is made of a single string, which keeps the name, and it is itself as well a singleton. There's only ever one instance of it. Now, as you notice, this is not a static singleton as you usually encounter it, but rather what we have dubbed an instant singleton. This is to allow you to easily use the multi-peer debug mode, which is a whole different subject. Suffice it to say that you should avoid static references wherever possible, because those can interfere with scalability down the road when you are in a server environment, or even locally if you attempt to run multiple clients and have them use different configurations. So, with that said, what does the player data actually do? Well, it checks the field, sees if the field is empty or not, and then assigns it. The important part here is that we make sure that this object doesn't get destroyed between scene loading. This will be necessary, and the why will present itself in a moment. Yes, Zachary, set active scene is the safer way when you're not ready to use additive loading or a more complex scene structure yet. It is, once you enter in production, not any more suitable usually because you have a more complex scene loading process. For instance, because you might want to load your UI from a separate scene rather than the scene where you have all your game objects located. But for prototyping and for starting, it is the quickest and safest option. Right, so now let's take a quick look at what we just discussed looks like from a diagram point of view to better understand the internal logic of how these various aspects communicate with one another. In here, we have the start menu. The role of the start menu is very simple. It's just an interface so that our buttons can call specific logic to be run on the simulation. One part is, as we just discussed, creating the actual player struct, which contains the player data, with in this case the nickname. Notice that the player data itself currently is not networked. It is just a local object because it just contains information that is local to the player that they have control over. It has not been yet communicated to the game session. This will be the next step in a moment. The other part is, of course, as we discussed, create the network runner. In our case, the network runner is composed of the network runner component, a local input poller, as well as a script called onServerDisconnect, which handles the return to the menu if the game session were to disconnect for any given reason. This is very straightforward, and this is sufficient to start having a menu that you can control and have players start testing sessions, whether it is internally or publicly. Now, let's switch to the next scene. The scene that you're probably all here for, which is, well, the game scene. After all, there is no point in connecting to a game session if there is no gameplay, is there? So, the game scene itself is fairly straightforward as well. However, before we dive into it, we will look at the actual logic of how the different systems in gameplay communicate, as there's an extra level of complexity here before we dive into the different scripts. So, let's go back to Mira for a second. These are the different aspects of our gameplay scene. As you will notice, the actual UI aspect here is very small. And more importantly, it is completely separated from the game state, or rather the gameplay simulation, because the UI itself only needs to be informed of what has changed in the game state rather than constantly try to understand what the game state is. The UI, after all, is just there as an interface to display what the game state is to whoever actually, like ourselves, only has eyes and can see the information on the screen rather than read the memory itself. This means we currently now have different systems. And as any good Asteroid game, it starts with the actual Asteroid spawner. The Asteroid spawner itself is, here again, an instance singleton and has the only responsibility of spawning an asteroid and initializing any data the asteroid needs to know about itself and the clients need to know about the asteroid. What do we actually need on the asteroid in order for it to behave? Well, first one is it a large asteroid? A large asteroid will break into smaller asteroid if it gets hit. And of course, its behavior is just a movement across the screen, which means it also needs to check whether it is still on screen in order to be able to despawn itself, since we don't want to just create thousands of asteroids that never get despawned. Now that we have the asteroids, the next most important thing is, of course, checking what does the asteroid actually confront. And that is the player. The player controls a ship that itself is created by the spaceship spawner. Now, the spaceship spawner does two things. Number one, it actually finds the spawn points. The spawn points are just empty game objects with a spawn point component so that they can be identified as such in code. The spawning is then itself handled by the spawner if a player joins late or the game has started. And then finally, of course, it handles the despawning of the ships to be a complete circle. Now, the spaceship itself is made of multiple components. The first one is, of course, the controller itself, which handles the ship state. Is it alive? Is it dead? The next one is the movement controller, which consumes the input in order to move from left to right and rotate. And accelerate, of course. Finally, we have also the visuals controller. Now, this is a particular one because it literally only handles the visual part of the spaceship. And then finally, we do have the fire controller to shoot our dear bullets to kill the asteroids, as well as the networked version of the data associated with that particular player. As you see here, we have the actual nickname, and then of course, two aspects that are specific to the game itself, the score and the lives. All right, with this in mind, let's take a quick look at how these two things are actually built. If we go to our spaceship scene here, we will see the object over here. So in order to, again, keep simplicity front and center in this example, we are just using a rigid body to move the ship across the screen. It is not a character controller, but just a physics object. In order to network a rigid body using Fusion, you need one single script, or rather two scripts, as a matter of fact. You need a network object to give it its identity on the network that all network data requires. And then we need the network rigid body, which is a pre-built component we make available to synchronize the state of a rigid body across clients. It is also here that you will notice the interpolation target. The reason why the interpolation target is separate from the actual rigid body itself is because this rigid body will be affected by the simulation, meaning it will update at whatever the tick rate is of your Fusion simulation. However, that might not be completely smooth because you will have rollbacks, you will have predictions, you will have mispredictions, and error correction. So, to make it smoother, the model itself is nested as a child and then only interpolated between the various results. Okay, now let's dive into the player network data before we go into the different behaviors themselves. The player network data, as I mentioned originally, is simply said the networked version of our player data. This means we have the nickname over here, which we have defined as a network string and limited to 16 characters. A network string always has to specify how long at the maximum it is due to memory allocation concerns. And then of course we have the lives and the scores. To get the nickname and inform the host what our chosen name is, we simply in spawn, which is called anytime an object is replicated locally on your client, whether the input authority of this object exists. All the proxies, meaning all the objects that the client does not have control over, will not have input authority over. That is why we use this check. If this client has actually, as we said, input authority over the object, we decide, okay, let's find our player data. Now, we read, of course, the nickname from it, and then send this information via a one-time RPC to the host to inform them of it. Of course, we do our regular safety check, and then the host, which is the only simulation which has state authority over all the objects, meaning it can actually change the game state, well then officially changes the existing nickname, which is null, to the nickname that we have provided. However, the question here now of course becomes, great, it's been changed. But how do we reflect this change on the various UI elements? Well, for this, because these changes are one-off and infrequent, we can simply use the onChange callback. To provide an onChange callback to a parameter, we decide in the network attribute onChanged should be, for this particular instance, call this method. Now, this one will then inform the overview panel, which we have referenced in spawned, and inform it about the nickname to update. The same procedure is the one used to update the score and the lies in the UI. All of these will be called locally. These are not RPCs. Anytime the simulation detects after all of the ticks have been simulated and re-simulated, more importantly, after receiving a snapshot from the server, they check whether that variable has changed. If it has, onChange is called, and it can be used to display visuals or update UI elements. It should not, under any circumstances, be used for gameplay, as it might be missed. So, as we said before here, that is what we update using the actual local decision from the client that controls this object. Or rather, that can provide input for this object. The host, on the other hand, has authority over it, which means they can initialize the networked variables. And so here, they of course set the score to 0 and give them the starting lives. As you see, this section here will exclusively run on the host, whereas this one will only run on the client with input authority. However, the UI itself, of course, needs to be updated on all the clients, and the UI is local. So, in order to do that, we will cache a local reference to our player object, or rather, the player overview panel over here. And of course, once this is done, inform the panel that, hey, this player data network exists. Please register us as an entry on the UI. Great. So that allows us to now move back to the actual behavior of the spaceship. Before we dive into the different controllers, you will already notice two different colors. Colors that I did not actually choose, but rather that are provided to make it easier to identify whether what you are about to look at is a simulation behavior or a network behavior. A network behavior can contain network state, whereas a simulation behavior cannot. Both of these are tied to the Fusion simulation and can execute on rollbacks and prediction and have access to the fixed update network function, which we will be seeing a lot of in the common scripts. So let's start with the Spaceship controller. The Spaceship controller only has one networked variable, the respawn time, because that is actually no, two, sorry, is alive and the respawn timer, because those are the two only aspects that are its network state that is necessary. All of the other things that we see here are local references, just like the ones that we just discussed, and these ones are settings. So these will not change and will be defined when you build it. So just like before, we set our local runtime references, and if this is the host, so all the clients will have no state authority over the objects, only the host does have state authority, and then we set it, of course, to alive. Over here, we have the callback whenever the state changes. And when the spaceship is brought to life, of course, you want to trigger the visuals and toggle them on. And if they were off, you want to turn them off. This is where the magic happens. And as you see here, it simply calls the method on the visual controller. We will get to that in a moment. In fixed update network, we have the methods affecting the logic that is networked itself, meaning, do we need to respawn once the time has expired? And of course, most importantly, have we hit an asteroid? Because if we do, we need to, well, destroy the ship and start the respawn counter. This we do simply through a overlap shape, or rather overlap sphere here in lag compensation. Now, this could, for a game like such, be a regular physics call, but in this case, it gives us a little bit more wiggle room to be accurate on the client side. If we do hit an asteroid, we of course tell the asteroid that the ship hit it and return true, which then will trigger the respawn routine over here and deactivate the ship during that time. So let's move on to this. Of course, when we reset the ship, we simply set the velocity to 0. And that is it. The controller itself does not do anything more than control the most important parts of the ship, which is, can it be controlled and is it alive? Now, we can move on to the next one, which is the player ship visual controller. The visual controller does, as we mentioned before, just one thing. It toggles the visuals on or off, as we see here in spawn and destruction, and starts or stops the respective particles for the destruction or the engine, depending on the state it's in. That is it. Now, we have made it a simulation behavior in order to be able to inherit from iSpawned, because we would only want to initialize the actual renderers and everything once the object itself has been spawned, and therefore this is just convenient. The next part is, of course, the movement controller. Now, the movement controller does not need to be networked because, well, rather, it does not need to carry state. As we saw, it was green, and that was because it too is just a simulation behavior. It is a simulation behavior because it affects simply the network rigid body, which carries the actual state of the movement. And so here in fixed update network, which is where all logic happens as per usual, we check whether the controller for this spaceship accepts input for one, and then if it does, we do try to get the input for that player. And then we simply apply it to the rigid body using our defined calculations. In case it exits the screen, we simply make it wrap around and come out the other side. That is it. Now, there is one more part, of course, in the spaceship itself, which is the fire controller. The fire controller does one thing, and it simply checks whether or not the spaceship should fire a bullet. For this, we have several things. First, of course, the setting of what is the delay between the shots. and of course a reference to the actual bullet. Now notice here, we are using a network prefab ref. This is essentially the same as a game object reference, but it narrows it down to network objects. This is very convenient as it allows you to use the Unity Inspector's find asset feature in the editor and simply find the network object prefabs you have in your project rather than to have to find anything at all. Yes, Zachary, I noticed. Thank you for the heads up. So when we fire the bullets, assuming we do accept input, of course, we want to know whether a button was just pressed. Now, a button was pressed if its previous state has changed from its current state. And in order to make this easy for everybody, we have created the network button type, which comes with some handy methods to check, okay, whether the current buttons that we have passed in, or rather the previous buttons are different from the current ones. And then it returns the state that we want, which we can check using was pressed and the actual button, which is the perfect time now as well to look at the definition of our own input. Of course, the bullet itself is fired if it was pressed, and in this case, if the timer itself had expired already. At which point we spawn the bullet and set the timer to the actual delay. So, what is our spaceship input? It is one float for the horizontal input, one float for the vertical input, and network buttons for the different buttons you could press. In this case, we only have a single one, which is fire. This is the struct that will be filled out every tick and sent to the host from the client after their input has been polled. The input itself is always polled only locally. Clients do not know of each other's input. It is only known to the host, who will consume it and then use it to decide the final state of the game. Now, this is why we can have the input poller to be completely local and a mono behavior. It implements the iNetwork runner callbacks, since it does need to be called by the runner itself. This gets automatically registered if the script is on the same object, on the same level in the hierarchy as the network runner, which it is in our case. When our input is called, we simply create a new struct, read the value in our horizontal and vertical axes, and also check whether this button is down, or we simply get its state, and tell we want to set it for this button in particular. Pay attention here. As you notice, we don't use get button down or get button up. We read simply the state of the actual button. Whether it was pressed or released will be taken care of by our implementation in the Spaceship input script itself, because we want to be sure that the state was networked and that we read it properly. So when you read buttons, be sure to always get the state and not on down or on up. And then of course, we set the local input we had to the one the runner expects, and that will then be sent to the host for the simulation. Okay, so we have looked at our most important aspects. The bullet itself, we will look in a moment, at in a moment. It is very simple, but might be worth checking out quickly. We will not be looking at the spawn points because that is just an empty object. And we will not look at the star field because that is just a particle system. Now we will be moving to the two interesting aspects that you will need in order to control your UI and everything, which is the game state controller and the bullet, as this will trigger the actual points. So let's just start with the bullet and we will move to the game state controller in a moment. The bullet itself is just a network transform and a bullet behavior, which is again just a network behavior. It has its setting, which are local, its direction, which of course is networked, then we don't have to calculate it every time, and it travels in this case in a straight direction, and it has a tick timer for the current lifetime. Here again, we only initialize the actual networked values from the host, and all the clients just skip this part. In fixed optic network, we do check, okay, whether we've hit an asteroid. And here again, because we are on the client side, a lot of the time, we use lag compensation, raycast to check, okay, did we hit anything? If we did, we inform the asteroid that we hit it, and we use the player reference of whomever shot the projectile to tell the asteroid you got hit by that player. And that is all it does. Let's take a quick look at the asteroid behavior to see how that handles it. As we previously mentioned, it simply knows whether it's a big asteroid or not. And of course, how many points it gets, or rather, it assigns when it gets broken. If it's a big asteroid, it tells the asteroid spawner to break up into smaller pieces at this position, which will then spawn smaller asteroids that spin, and you can get points for as well. And if it was hit by a projectile which provided it with a player ref, it will then call the player data network to add points to the score. Now keep in mind that this only happens on the host because, again, the host is the only one who can change the state of the game. When the score is updated, on-score change is called, which then itself updates the overview panel and therefore the UI. Right, so now let's move on to the game state controller. The game state controller has one single but very important purpose, that is knowing what the state of the session is, meaning is it currently starting, is it running, or is it ending? Now, during these three states, different things will happen. During the start delay, it will simply present the user with a countdown until the game starts and tell, okay, that's how much time is remaining until asteroids start spawning. Once this has happened, it will also tell, because the game has started now, the asteroid spawner and the spaceship spawner to start spawning. During the updates, or when the game session is running, it simply does present the timer for the whole game session. And finally, the most important part, which is during the ending, it checks, okay, who is left, who is the winner, and then present that. The check for whether or not the game has ended is also done by the game state controller. First, it checks whether or not more than one player is alive. If more than one player is alive, the game has not ended yet. If, however, only one player is left alive, it checks which one it is and declares the winner. And that is all it does. Now, let's move on to the final part, which is the actual overview panel of the simulation. If we take a look at this, it is just a canvas that literally just has the player name, the score, and the lives. This is updated by the player overview script, which, as we mentioned before, is purely local. Therefore, it does not need to be networked. And here it holds a reference to the player names, to the scores, and to their lives, always using the player ref as a key in order to be able to associate a specific client with its specific data. These are kept separate simply because it is easier to iterate over. And of course, in your case, you could put them together or do your own data structure. If we look at the add entry and remove entry methods, we see that it just instantiates it, resets the information, and adds the player ref with their current information to its dictionaries. Same goes in the opposite way for the remove entry. We simply remove the references and destroy the entry. For each of these, we update the actual information. And as we saw, this is being called from our player data network script. We give it the information, the UI updates the information that it currently has in store, and then it updates the actual entry by simply combining the string and displaying it to the players. This is the complete information of the sample. This is also the only information that you need to have in order to get started with Fusion. I hope you will have the time to dig into it yourself. The sample is available over on our website, of course. Link is in the description. And I wish you happy coding. Now, of course, if you still have a couple of questions, I'm available to you. And otherwise, I would highly recommend you join our community Discord, where we have an active community as well as some of our developers who try to answer as often as they can. All right then, looks like we're out of question. Thank you very much all for your time, and I wish you a great weekend. Talk to you soon, and happy developing.